So like he said, I'm Nicole Fields. Can you guys all hear me? I sound really loud to myself. Okay, so I'm a grad student at the University of Chicago. I just finished up my 5th year, and I'm going to talk about COSI, which is Coherent Neutrino Scattering with Cesium Iodide, and this is basically my thesis work. So first I want to put my acknowledgements up front. I really want to thank my advisor. This is entirely his idea, and it's really a really good idea, and it's a hard thing to do, and so people have been trying to do this sort of thing for a long time, and no one's been successful yet. So it's definitely a lot of credit goes to him. Our collaborators at Pacific Northwest National Lab, they've done a lot of things, and they've provided us with a lot of the material that we've used in this. We've actually just started a new collaboration. So these are our proto-collaborators for coherent scattering interactions at the SNS, which had a meeting early this month, and it was really productive. Also, the Kavli Institute for Cosmological Physics at the University of Chicago, they provide us with a lot of resources. Obviously, the Stewardship Science Graduate Fellowship, they've given me a lot of opportunities, and they basically allow this work to happen, and Krell for running the whole thing and being really great. Okay, so just a quick outline. I'm going to talk about coherent neutrino scattering, sort of what it is. It's predicted by the standard model of particle physics. I'm going to talk a little bit about that, and then I'm going to talk about why it's interesting and why we want to look at it. I'm going to talk then sort of about the Spallation Neutron Source, and basically how we want to use it as a high flux neutrino source, which no one has sort of used it for yet. But it's a really interesting possibility. And then I'll sort of talk more about my thesis, COSI itself, the experimental design, and sort of where we are and what our status is. Okay, so coherent neutrino scattering. What is it? Well, you have a neutrino and you have a nucleus, and the neutrino comes in, it hits the nucleus recoils, the neutrino goes out. No inelastic scattering, no excitation of levels, nothing like that. There are 3 neutrino flavors that I think Josh mentioned yesterday. So nu e, nu mu, and nu tau, and all of their anti-flavors, and they all scatter exactly the same way. It's Z exchange. It's really standard. So this is elastic neutrino nucleus scattering. And the important thing, I think, is, yeah, okay. So here is sort of the maximum recoil energy that you can expect. So if you have a neutrino of some energy, you have some mass of your nucleus, this is the most energy you can see. And so if you have a detector, that's what you see. It's a nuclear recoil, so it's similar to things like dark matter, neutrinos, beta decay, stuff like that. So you're really looking for nuclear recoil as opposed to electron recoils. And there you can see the Feynman diagram, the neutrino comes in, it exchanges a Z boson, and the nucleus recoils. So what about coherent elastic neutrino nucleus scattering? Well, so this is a little bit different. So if you have neutrinos of the right energy, and here the right energy means, say, less than 50 MeV, then the neutrino doesn't interact with just a proton or a neutron. Instead, it interacts with the whole nucleus because the wavelength is basically too big for it to see the individual nucleons. And so here we're talking about recoil energies that order 10 keV NR. And so NR here is nuclear recoil as opposed to electron equivalent. So if you see keV EE anywhere, that's electrons. There are no free parameters. There's nothing to measure. There's no mixing angles or anything like that, which you see with a lot of neutrino projects. It's entirely predicted. You know exactly what you're looking for. And importantly, it's the highest neutrino cross-section in the standard model. If you want a neutrino to really interact with your detector, you really want it to be coherent, it bumps up the cross-section by a lot. I'll talk about that in a little bit. And it's really not controversial. Nobody doesn't expect this to be here. When you calculate dark matter cross-sections, its coherence is assumed. Everybody thinks that this is right. Nobody expects it not to be there, but no one's measured it because it's hard. The 10 keV/NR recoil is really sort of tricky to see, and you need a really sort of low threshold detector to do it. So this is the mathiest slide, I promise. So here's the differential cross-section. G is the Fermi constant, E nu is the neutrino energy, cosine theta is the angle at which the neutrino recoil scatters. Q weak is the weak charge, and then this F here is the form factor. So that's a nuclear form factor. So that's really where you say, this is where we say, okay, eventually we're going to lose coherence because the momentum transfer is too big. So we really want to be talking about sort of low momentum transfer. And then Q there is the momentum transfer. And so this weak charge here is basically how it interacts with the weak force and how it exchanges the Z boson. It turns out that this theta W here is the Weinberg angle. So N is the number of neutrons, Z is the number of protons, and theta W is the Weinberg angle. So sine squared theta W is 0.23, and so basically the proton part cancels out. So you're really only talking about neutrons. But in the end, your whole differential cross-section goes like n squared. So the more neutrons you have, the better off you are, the higher your cross-section. And that can be an enormous enhancement. You know, we're talking factors of 100 squared, say. And so coherent neutrino scattering is really interesting. If we could see it, we could do a lot of interesting things with it. People are interested in it for supernova neutrinos. They're sort of the right energy. You could see them. You could basically see a supernova with a smallish detector instead of the sort of ton-scale detector that people are talking about. Interesting, probably to a lot of people here, is nuclear reactor monitoring. You know, this is the stewardship science part. You want to see coherent neutrino scattering because you want to use it for applications. Reactors are a little bit harder, and I'll talk about that in a little bit. You could look for non-standard interactions. Everything is totally predicted, and so if you see something that you didn't really expect to see, that could give you information about the standard model. People are sort of really interested in sterile neutrinos. There's a bunch of sort of tantalizing hints of sterile neutrinos that many people don't actually believe. But sterile neutrinos don't interact via Z boson, so they won't interact in this process, and so you won't see them. So if you have a neutrino, it becomes a sterile neutrino, say, it won't interact this way, and you can measure that potentially. It's a sensitive probe of the weak charge, and neutrinos are predicted to have a magnetic moment in the standard model, and the current bounds are about 10 orders of magnitude higher than the standard model prediction. So you could potentially look for something like that. Okay, so I'm going to switch gears a little bit and talk about the Spallation Neutron Source. So the Spallation Neutron Source is located at Oak Ridge National Lab. There's a picture of it. It's the most intense pulse neutron beams in the world. That's their claim to fame. But we're really sort of interested in using the Spallation Neutron Source for neutrino science. And this is a thing that Oak Ridge is also interested in, although no one has actually managed to do yet. And so this is just sort of a layout, which I stole from Oak Ridge. And you can sort of see, we took the tour of Lance, the fellows, on Monday, and you can sort of see it's kind of the same idea. You have an ion source, you have a LINEC, you have a ring, they bunch the protons, they chop them, they do all of these very interesting things and all of this accelerator physics. And this is sort of the target hall, and it hits in here, there's a liquid mercury target, and you make neutrons. You make lots and lots and lots of neutrons, and that's what they use it for. There's this whole nice facility and support and everything. But we're not really interested in the neutrons. So I'm going to talk a little bit about the SNS Proton Beam, because essentially to make a high flux neutrino source, you really need a proton beam. And the SNS Proton Beam is great. It's got 1 GeV protons, and that might seem like not a lot considering you have things like the LHC. But 1 GeV protons are perfect. They make lots of pions, and that's really what you want. In fact, the SNS is thinking about an energy upgrade, and for our purposes, we wish they would just stay at 1 GeV protons. Even a little lower in energy would be great, sort of like 800 MeV like the Lance beam is. It's a liquid mercury target. That's standard to use a high Z material. Lance uses tungsten, but basically you take a bunch of protons, you hit a target, you make lots of neutrons. And so the protons come in 700 nanosecond bunches at 60 hertz. The important thing is this gives you a duty factor of 4 times 10 to the minus 5. How many times you're looking at protons and how many times you're looking at nothing, this is sort of a ratio. And what you really want is for this to be really low. You would like to basically be able to say, look, and basically this is related to your background rejection factor. So the more you can say, look, the neutrinos only come here, I only have to look there, I can reject all of this other stuff, that's really good. So the SNS has been operating between 0.8 and a megawatt since 2009. The design operation, I think, is 1.4 megawatts. There's a possibility that they could get even more protons, which would be great, but this is sort of their current operating conditions. And they operate about 8 months a year. So they're on for 4 months, they're off for 2. Ideally, we'd like to be running when they're on, but it's a good idea to basically say, well, what other backgrounds would we have with the SNS, although you can do background measurements in situ because of this duty factor, because a lot of the time the SNS isn't giving you protons. Okay, so how do we get pions out of protons, and how do we get neutrinos out of pions? Well, this is all really very standard model particle physics. These are the neutrinos that the SNS gives you. They're called decay at rest pions, Anytime you have protons and you get pions, these are the neutrinos you get. They're very well established. So you have protons, they hit Mercury, they make a bunch of neutrons. You don't care about that for this purposes. You make pions. And you actually make both kinds of pions, pi minuses and pi pluses. The pi minuses all get absorbed. We're not going to worry about them for now. So you have this pi plus. It decays to a muon and a muon neutrino. And this happens really fast, 26 nanosecond lifetime. Remember, the bunches are 700 nanoseconds long. You can't see that. It's basically instantaneous with the beam. So then you have these muons. They decay to electrons. You get anti-muon neutrinos, and you get electron neutrinos. And the muon has a 2.2 microsecond lifetime. This is sort of well known. And so if you look over in this plot, the muon neutrinos here are prompt, and these electron neutrinos and these anti-muon neutrinos are delayed with some half-life. And just to give you sort of an idea, I did this calculation earlier. 1 megawatt of beam at 1 GeV gives you 6 times 10 to the 15 protons per second. And you basically get an order of magnitude down in the pion production. But for each pion, you get 3 neutrinos. So the protons and the neutrinos are roughly the same flux, about. And so here are their energy spectrum, and as I said, we need energy sort of less than 50 MeV or so to do coherent neutrino scattering. Luckily for us, the cutoff is 52.8 MeV. And the prompt neutrinos have this nice line. So you don't even have to worry about the fact that they're at different energies and will interact differently. Although if you can observe all 3 neutrino species, that would increase your statistics. And I know some people do things with reactors, and people have tried to look for coherent neutrino scattering at reactors before. Another experiment I'm on called Cogent did exactly that and didn't see it. But so why would you want to use the SNS instead of reactors? Reactors are great, right? We want to use them for nuclear reactor monitoring. Why not just go there? Well, so the bad thing about the SNS is that the neutrino flux is down by 5 orders of magnitude. Reactors have a lot of neutrinos. The SNS, not so many neutrinos. That's the only downside. This pulse structure basically gives you a rejection on your background of non-beam related backgrounds by 6 times 10 to the minus 4. So that's saying I trigger at 60 hertz. I look at 10 microseconds, so I get all of the muon neutrinos, the neutrinos from the muon decay, and I get a really great background rejection. That means my experiment doesn't have to be that low background, because I get this great background rejection factor. You can do background subtraction because you have beam on and beam off all the time. And the really important thing is that your neutrinos are more energetic. So these neutrinos go up to 50 MeV. Reactor neutrinos goes up to about 5 MeV. And so that factor of 10 directly impacts the recoil energies that you can see. And so it's really hard to see small recoil energies. So the more energy your neutrino has, you trade a little bit in cross-section, but you gain a lot in recoil energy. You also have 3 neutrino flavors, so you're not worried about strange neutrino effects like that. But you do have to worry about beam-related backgrounds. They make lots of neutrons, which is great. They're a background. We worry about them. We worry about how much shielding we'd have to put between our detector and the neutrons that they're making. And so that's a thing that doesn't really happen so much at reactors. Okay, so let's talk about COSY. So COSY is my thesis. There's a lot of work that I've put into this. It's probably a lot more work than I can really show you here. And so this is where all of my time has been spent mostly. So let's just talk about cesium iodide. So we want to use cesium iodide, sodium doped. The standard cesium iodide is thallium doped. So in some ways they're similar, but in some ways they're different, and I'm going to talk about that a little bit. So cesium iodide is an inorganic scintillator. Its peak wavelength emission is 420 nanometers, and you can see this plot. It peaks right here. Thallium peaks a little bit higher. It's transparent, so you don't have to worry about getting all the scintillation light out of your crystal. They're clear. I'll show you a picture. It's got a 630 nanosecond decay time. It's a little long for inorganic scintillators, but remember the muon lifetime is 2.2 microseconds, or shorter than that. That should be good enough. It's really high photon yield. It's almost as high as sodium iodide, which is sort of the standard go-to inorganic scintillator. 64 photons per keV EE. So this is electron equivalent, and before I was talking about recoil energy. There's a minimal afterglow. So afterglow is what happens when you have a really energetic event in your crystal, and then milliseconds later, you're getting single photoelectrons from that muon event. So thallium has really bad afterglow. You can't do single photoelectron counting experiments if you have lots of afterglow. Cesium doped sodium, cesium iodide sodium doped has much more minimal afterglow, and we're less worried about that. Also, if you can increase your overburden even a little bit to muons, this problem gets even better. It's mildly hygroscopic, so you can't just leave it out. You have to encapsulate it, but that's totally feasible. Okay, so why do we want to use cesium iodide sodium doped for coherent elastic neutrino nucleus scattering? So here's a picture of my prototype crystal when it was being encapsulated. So first and foremost, lots of neutrons. Lots of neutrons, cross-section goes like n squared, really high cross-section. That's what we're looking for. Another sort of nice feature, although not required, is that cesium and iodide are really close in mass. So they basically act like a single recoiling species, and you don't have to worry about, well, first I scatter off my light nuclei and then off my heavy nuclei. They're basically the same thing, and you can treat them as if they're the same species. We know that we can make these crystals low background. Well, why do we know that? Because people want to use them for dark matter. So if you want to use cesium iodide for dark matter, you better be able to make it low background. So that was a good thing. The Kim's collaboration is using cesium iodide thallium doped. And so we basically used their background measurements to say, okay, look, we can get about these sort of background rates. That 420 nanometers that I mentioned, the scintillation is really well matched to PMT, and that's what you're going to stick on this thing. So you really want to get as much quantum efficiency as possible. You don't want to lose a bunch of photons because your PMT isn't going to see them. And it's not that expensive. It's sort of about a kilobuck per kilogram. So that's sort of a handleable amount of money. So this is a prototype crystal. It's 2 kilograms. This is its encapsulation. You can see here, it's clear. You're seeing all the way down to the Teflon reflector. We screened the salts for this crystal before we grew it. We basically didn't see anything in them. And now we're taking background runs with the full crystal. The copper can is electroformed. Pions did this for us. This is basically the best way to make clean copper. And it's a good way to do it because it turns out it's cheaper than buying a big chunk of copper and machining out the middle. All of the other copper pieces, the flanges and the rods and everything, that's all oxygen-free high conductivity copper, which is commercially available. The window here is synthetic quartz. That's also pretty clean. We also counted that. We screened all of the materials. I screened all the materials in our low background counting facility at UChicago. And basically just to make sure that we weren't putting anything really radioactive near our crystal. This PMT is an ultra low background PMT. It's about 7 or 8 years old. It has some PMT issues, but it works fine for these purposes. And here you can see that this is 2 inches of low background lead. And so the PMT base is on the other side of 2 inches of lead. PMT bases tend to be pretty radioactive because they have a printed circuit board in them, and that's got lots of nasty metals and stuff like that. And the interesting thing about this design is you have this PMT, you have these leads, which are flying leads, and they're insulated, and they go through 2 inches of grounded lead before meeting up with the base on the other side. And so that was a sort of nerve-wracking process to put this together, but it works. It's great. And it provides all of this shielding, and that's really important for us. Okay, so let's talk about sort of the general cozy design. This is sort of drawings of it. So from the inside out, we sort of have the crystal. This is a 15 kilogram crystal in this design. It's got 1 inch of ultra low background lead. Lead has lead-210 in it. That's radioactive. Standard lead bricks are 300 becquerels per kilogram. And so ultra low background lead is less than 0.02 becquerels per kilogram. So that's great. We have it right near the detector. Then you have 6 inches of regular lead. You have boron flux, which basically absorbs thermal neutrons. Neutrons can be a background, and you want to sort of get rid of some of them. Then we have a 7-panel muon veto, which is 2 inches of plastic scintillator. It's hard to see in this picture. I don't think it's possible, but it's actually a hexagonal shape. And so we have 6 panels that make the hexagon and 1 round panel on top. We have cadmium underneath the detector. That's also for neutron capture. And then outside of that, we have this high-density polyethylene, and that is for neutron moderation. So you basically take ambient neutrons, you moderate them, you capture them, and then you hope they don't hit your detector on the way in. And this is the pipe right here, and so it all fits into this big pipe, so you can just sort of move it around, and it makes it very transportable and compact. This whole thing, I guess, is about as tall as me. And this design, the shield design, accepts up to a 15 kilogram crystal. So that's what we really want to use. We only have a 2 kilogram crystal. We've stuck it in this shield. We're doing measurements. But to go from a 2 kilogram crystal to a 15 kilogram crystal, all you need is the crystal. Everything else is exactly the same. So here's the latest progress. This is a picture of it in the lab at U Chicago. All of those lead bricks, and there are like 300 lead bricks, they've all been etched with nitric acid and hydrogen peroxide. So the entire shield has been cleaned. I never want to have to do that again. But that's been done, and we've taken background runs, and they look good, so that should be good enough. This muon veto, which I also built, is 99.6% efficient. And so basically what you have is you have a muon, it goes through 2 inches of plastic scintillator, it's going to leave like 10 MeV in that scintillator, and then when you get an event in your central scintillator, you're like, well, it was a muon, or a neutron, because muons make neutrons. And so it's a way to tag backgrounds and reject them. There's a 0.4% inefficiency, and that's basically a geometry factor. Maybe a muon gets in through the crack and hits the central scintillator, and your muon veto didn't get enough light at any one panel to trigger. And we're currently taking background data. I've taken on quite a lot of background data, but there's still some stuff to be done. And so since I spent a lot of time on this muon veto, I just wanted to put one slide on it. So we have these 2 inches thick plastic scintillator panels. There are 6 side panels. These white things are polyethylene on the outside, so the sort of black thing in there, those are the panels. So there's 6 side panels and 1 top panel. They have really good gamma muon separation. It's really hard to get bad gamma muon separation with 2 inches of plastic. So a muon is a minimum ionizing particle. It leaves 2 MeV per centimeter, so that's 10 MeV, and gamma rays only go up to 2.5 MeV. So you get really good separation. You can really say, look, we got all the muons. The trigger rate of the whole veto altogether is only about 300 hertz, which is really good. It limits your dead time. The dead time for this setup is about 0.5%. So it doesn't really affect the data taking very much. And sort of the nice thing now is that each panel, you don't see any PMTs, right? Because the PMTs are actually inside the panel. So all the panels have holes drilled into them, and the PMTs are potted inside the panels, which means you never have to touch the PMTs again. And you don't have to worry about breaking them or knocking into them or anything like that. And the panels actually protect the PMTs. They're also gain matched, so you're not worried about which corner of the panel you hit versus your light collection. And each of the panels is wired, so you have 1 signal and 1 high voltage channel per panel. 7 panels, 7 channels, which is a handleable number of channels. So I just wanted to show some sort of preliminary background measurements that I've made. This is with a multi-channel analyzer. So you take the PMT signal, you preamplify it, you shape it, and you stick it into a multi-channel analyzer. It gives you a bunch of numbers out. It gives you this spectrum. So this is basically the same exposure, which is 3 days or so. This is a log scale. And you can see this is with no muon veto. So this is if we don't veto any of our events at all. You can see here, this is the thallium cutoff. So in energy, this is like 2.5 MeV. Look at all of those muons. That's a lot of muons. This is run under 6 meters of water equivalent. We already cut down the neutron flux, the muon flux by about a factor of 3. That's a lot of muons. This is how many muons we get after veto. So this sort of basically shows you the efficiency. The efficiency is really good, and this is really sort of important. And you can also see that we have all of these peaks in the spectrum, and that's sort of external radiation from, say, the PMT or the epoxies that we use or things like that. This is the thallium cutoff. You see here in the muon veto in the non-muon veto spectrum, there's this peak, and you don't see it down there. That's the 511s because muons will make pair production, so you get a lot of that. And but you can still see that you see basically all the same peaks in this spectrum as you see in this spectrum. That's sort of a good indication that you're sort of doing it right. Okay, so then we take data with an MCA, and that's great. And we then do preliminary data acquisition background measurements because we're going to be taking data with a data acquisition system, and we want to basically see how the system performs. And so this is sort of that same spectrum made out of different DAC card ranges. And you put that together, and you can see that the background in counts per keVe per kilogram day is sort of handleable, sort of 20 or so. And as you go to a bigger crystal, you actually get some improvement because the external lines will basically be now spread over a much bigger crystal, so your rates will go down. Okay, so we're doing a bunch of future work. We're basically looking into getting the 15 kilogram crystal very soon. We're screening materials for it now. Some somebody, maybe us, maybe some other people, need to measure the beam-related backgrounds of the SNS, especially neutrons. No one has measured that. We don't really know quite what to expect. There have been similar measurements done at places like Fermilab, and we sort of want to have an idea of what that's going to be like. I'm going to sort of take more background measurements. You can never have enough background measurements. We also need to do some sort of low-energy nuclear recoil calibration, so we're going to stick a neutron source in there and make some measurements. So those are my conclusions. Coherent neutrino scattering is great. No one's ever seen it. We're looking for it. The Spallation Neutron Source is a great place to do that. And COSY is really a detector technology that we haven't had to tweak very hard in order to get it to perform and be possible to do this measurement. So, thanks.